In this video, we will solve the two-dimensional free rotation. It is essentially just the one-dimensional translation in a circular universe. Let's review this translation in a one-dimensional universe. H psi equals E psi, and the potential energy is 0. Therefore, we just have the kinetic energy operator here. And we solve this Schrodinger equation. We have two solutions, e to the power of plus ikx and e to the power of negative ikx. What is k? K is the square root of 2me over h bar, and the square root of 2me is simply the magnitude of the momentum, because this E is equal to half mv squared when the potential energy is 0. So now we have a free particle moving in a circular one-dimensional universe. This is our particle. This is the center of the one-dimensional universe. The particle has a potential energy of 0 on this ring with a radius of r0, and this is called a rigid rotor. This x is replaced with Greek letter chi. Chi is the position of the particle. Chi is equal to r0 times theta, and we solve the Schrodinger equation again. The only difference is I replaced x with chi. And we have two solutions. Again, e to the power of plus ik chi and e to the power of negative ik chi. So chi is r0 times theta, and k is again the magnitude of momentum divided by h bar. So now we still have two solutions, and we know k is p over h bar. We know chi is r0 times theta. We plug in these two expressions, one for kappa, one for k, in the wave functions. And then we notice here we have momentum times the radius, momentum times the radius for the rotation. What's the physical meaning of that? It's just the angular momentum. And we have to resort to general physics. In general physics, we learned the momentum vector, the angular momentum vector is equal to the cross product of the r vector and the p vector. And in this example, because the r vector and p vector are always perpendicular to each other, we have this angular momentum simply equals r0 times this p. But the direction of the angular momentum is perpendicular to the plane of rotation. Alright, so now we can simplify these two wave functions. We know this p times r0 is simply the angular momentum, and then we define this L. This is the quantum number for rotation. We define this L to be the magnitude of the angular momentum divided by h bar here, and then the two wave functions are very simple. It's e to the power of il theta and e to the power of negative il theta. And then I'm going to prove this L must be an integer. And over here, L must be non-negative. So in the end, I will prove this L must be a non-negative integer. And because of the periodicity, so remember the wave function of the particle at theta should be equal to the wave function of the particle at theta plus 2 pi, because there's no difference between theta and theta plus 2 pi for the particle. So we use this equation, we plug in this wave function here, and then we have the same wave function, except this theta is replaced with theta plus 2 pi. Therefore, e to the power of I times L times 2 pi equals 1 if we divide both sides by simply this a plus times e to the power of plus il theta. And then we have to solve this equation. This is very easy. We know the real part is 1, the imaginary part is 0. And how do we solve this? These two equations hold true only if L is an integer. We used this psi plus wave function to prove that L must be an integer. Similarly, if you use psi minus, again, L must be an integer. So L must be a non-negative integer. Now we define m sub L to be plus minus L, and we have a more general solution. This wave function of this free rotation is simply the normalization factor A times e to the power of I times m sub L times theta. And again, m sub L can be positive or negative, and m sub L must be an integer. So recall in general chemistry, L is the quantum number for the three-dimensional angular momentum, and m sub L is the quantum number for the z component of the three-dimensional angular momentum. So in here, it's a little bit different. In here, L is used as the quantum number for the two-dimensional rotation, but still this m sub L is the z component of this angular momentum of two-dimensional rotation. But again, in this case, actually, it's fairly simple because the plane of the rotation is confined to be on just a two-dimensional circular plane. So therefore, this m sub L can only be plus minus L in this case. And in general chemistry, you learned m sub L can be negative L plus 1, all the way to L minus 1 and L, only because you are looking at a three-dimensional rotation of the electron about the nucleus. All right, enough said. We will determine the rotational energy for this two-dimensional rotation. How do we do that? Very simple. We just apply this Hamiltonian to psi. The potential energy is 0. This is just the kinetic energy. And this chi equals R0 times theta. We plug it in here. And then this I is simply the moment of inertia R0 times theta squared. And the result is simple. We get this eigenvalue times the wave function. The eigenvalue is m sub L squared times h bar squared over 2I. And m sub L can be plus minus L, and L is 0, 1, 2, 3, and so forth. And pay attention here. This rotation seems to be a two-dimensional rotation, and if we define this as x, this is y, so it's a rotation on the xy plane, and it seems to be a two-dimensional rotation. But in essence, this is a one-dimensional rotation because this R0 is a constant. There's only one variable, theta. Only theta changes. So essentially, you may call this one-dimensional rotation. And in the future, when we look at the statistical thermodynamics, if you have this one-dimensional rotation, the average kinetic energy is only 1/2 kBT.